Everyone. Welcome to this week's Crunch seminar. Today we have one speaker and one talk. Our speaker is Thomas de Jong, who's currently pursuing a PhD in Systems and Control at Eindhoven University of Technology under the supervision of Dr. Mircea Lazar and Professor Dr. Saip Whelan. He obtained his master's degree in the same field from Eindhoven University of Technology with thesis entitled Energy-Based Cooperative Distributed Model Predictive Control for Frequency Control in Microgrids. His current research focuses on data-driven predictive control for nonlinear systems. As part of his doctoral work, he has published and had accepted 5 scientific papers to the date. Thomas, thank you so much for your time today. We're all looking forward to your talk, and with this short introduction, you can start.
Yes, thank you for the nice introduction, and also thank you for having me at the Crunch seminar. So what I would like to show you in this talk is work I did together with Kamraj Shukla from Brown University and Mircea Lazar from Eindhoven University of Technology, where I'm also from, a university in the Netherlands. So let's get right into it. So I prepared this presentation to take about 45 minutes, so that in the end we have some time for questions, or feel free to ask questions also in between. And it consists basically of 5 parts, where in the first part I would like to give some background knowledge, specifically on the field of systems and control. I want to draw some similarities between the field of machine learning as well. Finally, I'm going into model predictive control there, which is the work that we did in this paper. And finally, I give some problem statement in part 1. So let's start with that. So consider the following scenario. So we have a dynamical system. So first, I would like to draw this similarity between machine learning and control. And what is then typically the case? If you want to learn a dynamical system like this, which is represented by a set of ODEs, having an input function, an output function, and some hidden state, like for example, the inverted pendulum. And what you typically have is a data set of input trajectories. So these are time trajectories of input functions that you apply to your system. You collect outputs from your system, and this together forms your data set, right? So in addition, if you want to learn a model, what you typically have is a model class. So you assume some structure of your model, like for example, a fully connected feed-forward neural network, like you can see here. And the objective now becomes, given this model structure and given the data set, what are the optimal parameters such that our model does good output predictions, so that the output data set predicted by our model is close to the output data set. So what is the difference in the control problem? Let's look into that now. So again, we have our dynamical system here. But now the problem is a little bit different. And so we are given some different things. What we assume now is that we are given the model. So the model has been trained. Note that here we have the optimal parameters. In addition, we have a reference signal, and this reference signal is our control objective. So if you think, for example, of the pendulum, this objective might be we would like to swing up the pendulum and stabilize it in the upwards position. And so the control problem then becomes, given the model, we would like to find an input function such that our output function gets close to this reference. So it is actually kind of an inverse problem. So that makes it slightly different than a model learning problem, right? But still, there are some similarities. And so specifically, if you look into control systems, we can classify them into 2 basic groups. The first one being open loop control, where really you try to solve sort of an inverse problem. So what is given in this case? we have a reference function, and the goal is to find an input for a system such that our output and the reference signal get as close as possible. This type of control has some pros and cons. So the first one, it acts before an error occurs. So it's quite fast. But on the other hand, it's not very robust against uncertainty. So if your inverse model is not very good, eventually you will drift. And you could see it like for example, juggling a ball with a blindfold on, because you do not actually observe the output. So that is why, in addition to open loop control, we also have closed loop control. And in closed loop control, you close the loop by measuring the output. So you take off the blindfold, you watch the ball, and based on this information, you take a control action. So the control action now actually acts on the error signal. And the error signal is simply the difference between the output and the desired output. So given to us is the reference and the output, and would like to find an input function such that these get close and such that the error goes to 0. And then we say that our system is stable. So the pros and cons for this are, so it is robust against uncertainty. It's more robust because if an error occurs, the controller will take this into account and try to minimize this error. But on the other hand, it only acts after the error occurs. So typically in practice, a control system is combined of a combination of these two approaches. So now some practical considerations of a control system. So a control system is typically implemented onto a digital electronic device, like for example, the Arduino here. And one property of such a digital electronic device is that it has a clock cycle. So it takes actions each sampling time. After this clock cycle, it can take a new action. And because of this, actually, you cannot generate a continuous function with such a control system. Actually, what you do is after each sampling time, you can take a new action and you keep this input function constant. Also, because of this clock cycle, we cannot actually observe the output at all times. So we can actually only observe it during the sampling times. And so in between these sampling times, we do not exactly know what's going on with our system. Okay, so now the goal of designing a controller is to design a stabilizing controller. So stable means that the error eventually goes to 0, right? And so a very popular choice nowadays is to use model predictive control. And that is also what we did and what we will look into now. So here you can see basically the same control scheme, but now I included these properties that we can only change the input at the sampling instances, and also that we can only observe the output at the sampling instances. And actually what a model predictive controller does is it combines this feed-forward and feedback control, and it does this by predicting into the future. So we have some assumptions on a future input sequence. It has some finite length. And with this input function, we will do some predictions. So we do this typically by making a model of our system. And so we make a discrete time model of our continuous time system because we are only interested in the output values at the sampling instances. And since we can only change our input also at the sampling instances, we can get away with a discrete time model. And the problem then becomes, so an MPC controller, when it's implemented online, what you do during each sampling instance is solve an optimization problem, where the optimization problem is subject to some constraints.
Can I ask, what is the time step here compared to TS, to the sampling?
Yeah, the time step is TS, so that's the length that these
So the time step is TS, okay.
Yeah, exactly. So if we now look into what an MPC controller does, and one approach to develop a prediction model is by making a single step model of your system. So this model then predicts one step into the future. And how you obtain multiple predictions into the future is by iterating the model, so simulating it basically. So given an initial condition and an input, you apply it to the prediction model, the single step one, you get your new state, you have your new input, you give it again to the prediction model, and so on and so forth. And you do this for a finite number of times, n. And n is called the prediction horizon. So this determines how far in the future we predict. And that is something you choose as an engineer. So how is this then implemented onto the system? So the procedure that such an MPC controller takes, we call it receding horizon optimization. And so now we will go step by step on into what happens actually when we do this. So imagine we are at some point in time. So this time is by k. It is the black solid line here. At this point, what you do is you do state measurement. So you know the current state of your system. And with this, you solve an optimization problem, predict an optimal input sequence into the future. And with this, you get the state sequence into the future. And so you now have a complete sequence of inputs. Then what we actually do to apply it to the system is we throw away the last part of the sequence. And we keep only the input sequence for one sampling time. This one is applied to the system. We move on a step in time. So the sampling, this duration is equal to the sampling time. So now we're at time step k plus 1, and we repeat the whole procedure. So we measure the new state, do a new prediction, throw away the sequence for the largest part, and only keep the first one, and we apply this again to our system. And so most people within the machine learning community that I know, they really like chess. So I thought it's good to draw the analogy between MPC and chess because it's actually very similar. I think you will also like MPC because of that. So if you're a good chess player, typically what you do is at each point in time, you observe the configuration of the board, so of the pieces on the board, right? This can be regarded kind of as the state of your system at that point. And what you do is you predict a couple of steps into the future. How many steps? That's the prediction horizon then. So from these predictions, you choose the optimal sequence, but you don't apply the full sequence. No, you only move one piece. So this will be the input of your system. And you wait then for the sampling time to pass by. And this is then what your opponent will do. Your opponent will do a move. The configuration changes. And after your opponent is finished, you will observe again the state of your system and repeat the whole procedure again. So in this way, they are quite similar, MPC and chess. So now to make it a bit more technical, how this is solved. So as I said, online, this MPC controller solves an optimization problem at each time step. And how this does it is as follows. So here you have an optimization problem with some constraints. We try to minimize a cost function, and this cost function tries to minimize the difference between the output and a reference signal. Typically, you also include the input because you don't want your input to become too large. And the constraints are the following. So this is your observation of the state. So you initialize your prediction model at the current measurement. And then with your prediction model, you predict into the future. And you do this for the entire prediction horizon. So this is basically a for loop which generates n constraints for your optimization problem. In addition, you might have some constraints on the inputs and outputs of your system. So for example, if you design a controller for a motor, and this motor can only deliver some force like 10 newtons, then you can incorporate this into constraints. And similar for the output, maybe you have some velocity limit, you have a robot arm and it cannot move too fast. you can then incorporate this in the output constraints. And so this optimization problem here is solved during each sampling instance. So it has to be quite fast. And so one of the main challenges with MPC that we are also trying to solve in this work is how can we obtain an accurate prediction model of our dynamical system. And since often a lot of data is available from our systems, we would like to utilize this and learn an accurate prediction model from data. And so now we will go into that. We utilize the deep operator networks for this to develop a prediction model. And now I will show you how we can combine this and do actually MPC with that prediction model then. So when we look at the dynamical system, so here's our dynamical system again, the ODE with input, state, output. It can actually be regarded as a nonlinear operator, and specifically a nonlinear operator that maps an initial condition, so the current state, plus some input function to an output function, or a state function if you measure the full state. So we are actually quite lucky because it has been shown that a specific type of neural network structure, namely the DeepONet, can approximate such nonlinear operators arbitrarily well. And so we would like to use this to learn our prediction model. So the goal becomes of this work, how can we combine the expressive power of the DeepONets to learn such operators of interest for us with model predictive control to now not only learn a model, but also control the system. So how can we do this? So how can you use the DeepONet to get multiple predictions in time, considering our case of the digital electronic device on which we implement our controller? So we can only change our input at the sampling instances. And so by doing this, actually the input becomes not a continuous function, but just a vector of real values, so a real vector. And we would like to find a mapping to outputs. So what we do is we put this sequence as an input to the branch network. So the input to the branch network simply becomes a real vector. And to the trunk network, we give as an input the initial condition. So how do we now achieve multiple predictions in time? That is by also in the trunk network putting in a time value. And this time value is equal to the sampling time times j, some integer, which we iterate over the prediction horizon. And by doing that, we get output predictions over multiple time steps. So how can we now implement this into an MPC scheme? We can do that as follows. So first, we train the model with our data sets. And then once the model is trained, the parameters are fixed, so the weights and biases are all fixed. Then this simply becomes a function that maps an input sequence and an initial condition plus this time value to an output. So we need to re-evaluate this constraint n times, so for each of our prediction steps into the future. So one thing to note here is that the DeepONet in its original form approximates scalar value functions. So the input function should be a scalar valued function, a continuous scalar valued function, and the output as well. However, a solution was proposed for this called the MIMO-ONet. So let's look into that now, how that looks. So it is basically the following. So consider here the case for an input with two system with two inputs and two outputs. Then for each input function, you need to add a new branch network. So input 1, input 2, you need to add a new branch network. For each output, you need to add P neurons in the output layer. So this is a fully connected layer without an activation function, so just a weight and a bias. But this is not necessarily ideal for our case because we want to use this prediction model to compute an input sequence online. So we would like this model to be have the lowest complexity possible because we need to solve this problem fast. So our question was, can we get away with something simpler in our specific case? And so we will look into that now. We developed the multi-step DeepONet, which is based on our simplified situation. So now the main result of our work comes. And to look into what is simple in our case, first let's look into the universal approximation theorem for operators. So as I said, this theorem states that any nonlinear operator which maps continuous functions, v, so v is a continuous function, into a continuous function. So in our case, that would be a continuous function of time to a continuous function of time again, right? So this is not exactly the case for us. We don't have a continuous input function. No, we just have a piecewise constant function, which we can only change at the sampling instances. Also, we might have multiple inputs. However, since we only have a piecewise constant function, we can exactly represent all of these inputs at all of the time steps simply by a real factor. So our input space is no longer the space of continuous functions. No, it's simply a real factor. Also, our output function is a little bit different because we fixed the time steps. So we fixed the sensor locations where we want to measure our output. So actually, it no longer becomes a continuous function of time. It only becomes a continuous function of the initial condition. So what we want to learn is a set of operators that map these real vector to continuous functions. And we need n times ny function operators, where n is the prediction horizon and ny is the number of outputs. So we actually have this simplified situation. And so because of that, we slightly adapted the universal approximation theorem to our case, where now the input should be just a vector, and the output should still be a continuous function. And we showed in our paper that this universal approximation theorem is true. If you want, we can discuss it afterwards, or you can read the paper, but I will not present all the details of the proof. But yeah, we showed that this is the case actually. Also, what we showed is, if you look at this expression here, it is actually the expression of the stacked DeepONet. However, what we also showed, which was not directly clear to me, is that you can just take the unstacked DeepONet, and if you remove some connections, then you can recover this DeepONet again. If you take the dimensions, of course, large enough. So actually, our universal approximation theorem is valid for both of them, for both of these architectures. Okay, so the main conclusion are as follows. We have our control system, which calculates an input by using sample and hold. So we can only change it at the sampling time. We keep it constant over the sampling time. And because of that, our input is actually not a function, but just a real vector. Also, we fixed the sensor location of the output because we can only measure the output at the sampling instances. So because of this, we had the simplified situation, and based on this universal approximation theorem that we proved, we came up with a new network structure, which is a bit more simple. And that's the following. So we can now put the entire input sequence for all our inputs just as input to the branch network. And there's no more need to add additional branch networks for multiple inputs. Also, we removed the time dependency here as input for the trunk network. And from that, we directly predict all of our outputs at all of the time steps. So how do we do that? let's just look into one of those functions, how it looks. So firstly, so here you have one of the outputs at TS, one of the sampling times. The first part here consists of this part, which is a fully connected layer consisting of simply a weight matrix and a bias factor, and it takes as input the output of the last hidden layer of the branch network. Secondly, we have the trunk network here. It takes as input this this vector, the output of the trunk net, and it's also just a fully connected linear layer. And so note also that the number of neurons in these layers need to be the same, so they need to be equal to P because we take the inner product between them, or the Einstein sum. So we simply repeat this for all the outputs, having the same vector for the trunk network, but different ones for each of the outputs for the branch network. So these are different, these parts of the equation, but these are always the same. And so by doing this, once we train the network, we again simply get a function, but now this function has no more time dependency and it predicts directly all the outputs. So it simply becomes one constraint, which is desirable when we try to solve this online. So one more question is then, why can we just use one network for the multiple outputs? Because I didn't really explain that. I explained how we get the outputs, but not why this is valid and why the universal approximation theorem still holds. And to show this, we need to look into the underlying basis of the DeepONet. So first, let's take the simpler case, just a simple feed-forward neural network. And then what is the case for such a network? So these are the hidden layers. So these have activation functions. And this is just an output layer, again, just a weight matrix and a bias factor multiplied by this vector. And for such networks, it's the case that the individual functions in the last hidden layer form a basis. So this is a set of linearly independent functions, actually. So our question was, and this was also how we came up with the idea of the multi-step DeepONet, was what is the underlying basis of the DeepONet? Because now you have two networks, and the outputs of these networks are combined by an inner product to generate a new output. So how does the underlying basis look like? So what we showed in the paper was that the basis actually looks like this. So as I said, this is a basis for a standard feed-forward network, but now we have two. So we have this basis vector, this vector of basis functions. And what we showed is that the DeepONet actually has also an underlying basis, which is constructed by taking the Kronecker product of these two vectors of basis functions. So you'll get actually a much larger basis vector of basis functions. So way more basis functions. So this part of the basis actually comes due to the weight in the output layer. So the weight matrix. And these, you get them into addition because of the bias factor in the output layer of both of the networks. But so with this, we show that the DeepONet also has an underlying basis. And now we can draw multiple outputs from this basis by simply taking linear combinations of the basis functions. And so the universal approximation theorem is still valid for our case. And we showed that actually each output is simply a linear combination of this basis. Okay, so we developed most of the theory now. So let's now look into some numerical examples to see everything in practice. So we consider three numerical examples, and we compare the standard DeepONet based NPC, so the one where you had the time value as input to the trunk network, which you iterate, and we compare that with our multi-step DeepONet based NPC, which in a single shot got the multi-step predictions. We compare these two on the default poles later, firstly, Secondly, we will look into the four-tank system. And finally, we put the multi-step DeepONet-based MPC to the test by applying it to a pendulum on a card system, which is quite a bit more challenging example. Okay, so the van der Pol oscillator has the following dynamics. So it's a nonlinear dynamical system. It's nonlinear because here you have this square term of the first state, and you also have this multiplication between the state. Here we have the input, which we try to control with our MPC controller. And it has this parameter mu equal to 1. So why did we choose it equal to 1? That is because in this case, the van der Pol oscillator has a limit cycle, and this makes it quite challenging to stabilize the system. So we wanted to test, can we stabilize a system which has such a limit cycle? So to do that, we first did an experiment where we generated the data. So we applied a multi-sign input to the van der Pol oscillator. This is simply a sum of sinusoidal functions where we vary the frequency and the phase shift, and we tune this amplitude such that if we look into the state space, that we covered large part of the state space. So this was the objective. We wanted to capture the behavior, so you need to cover a large part of the state space for this. Okay, so now let's look at the result. We used this data set from the previous slides. We trained a standard DeepONet and we trained a multi-step DeepONet. We actually also did an ablation study where we checked the number of neurons, the number of hidden layers, the number of neurons in the output layer. And from this, we chose an optimal one based on the lowest validation loss. And so what we found actually was that we needed 3 layers to get the lowest loss, each with 40 neurons in them. And in this output layer, so that's a linear layer, we only have 20 neurons. Additionally, we have a prediction horizon of 10, so we would like to predict 10 steps into the future with this network. And so what we found was during training, that actually it took a lot more time to train the traditional DeepONet model, where we iterate over this time value than the multi-step DeepONet. Also, with the exact same networks, the same data set, we obtained a lower training loss with the multi-step DeepONet and a lower validation loss. So now let's see what happens if we plug the trained models into the MPC scheme and we try to control the system. So here you can see that result. So as I said, we would like to break this limit cycle and simply stabilize the van der Pol oscillator at constant points. And these constant points are here the reference. So what we saw was that we were actually, with both controllers, able to stabilize the system. Also, we got quite a good performance. This is actually a point that was lying quite far outside of the data set. So nice to see that both controllers were still able to stabilize the system. However, if you look closely, we saw that the MPC or the multi-step DeepONet-based approach had a little bit better performance in general. You can also see that here in the table. So this is the absolute mean tracking error over the entire simulation. And this was quite a bit lower for the MS DeepONet. Also, it was slightly faster to solve the MS DeepONet MPC problem online. You can see the times it took for each sampling. So this is basically the time it took to compute one control action on average. Okay, so now let's look into the second example, which is the 4-tank process. So this is a higher dimensional system. This is why we chose it. It has 2 inputs, which are the pump pressures here. And it has 4 outputs, which are the water levels in the 4 tanks. Note also that all of these tanks have a hole at the bottom, so gravity wants to pull out the water of these tanks. So quite a challenging MIMO system to control in general. Also, it's non-linear because here you have the square roots of the states. And I will not show all the training results for brevity, but let's look at the control performance here. So again, we used similar dimensions for both networks. So 2 hidden layers, 20 neurons in each layer, 20 neurons in the output layer. And we used a slightly longer prediction horizon here. So we want to predict further into the future. And that's because this is quite a slow system. So that's why we did that. And then if you look at the training results, you see again exactly the same. It took quite a bit shorter to train the multi-step DeepONet than the traditional DeepONet for the exact same data set and similar dimensions. Also, you can see that the training loss and the validation loss are again lower. And we can again see this in the performance of the controller. So if you have a good model, it indicates that the control performance will also be better in general. So again, here you have the absolute mean tracking error, and you can see that it's quite a bit lower for the multi-step DeepONet. Computation times were actually quite similar. We were quite surprised by that, but it's still a bit shorter for the multi-step DeepONet. So we saw a general trend that our tailored multi-step DeepONet did a better job for control. So this does not mean that we can replace the DeepONet, no, because the DeepONet is actually able to approximate mappings from continuous functions to continuous functions, and our multi-step DeepONet is not able to do that. But it is tailored for control, and it is a more efficient choice for online computations. So to finally put the multi-step DeepONet to the test, we did one more example, which is quite a bit more challenging example. And it's challenging because it's very highly nonlinear. You see all these trigonometric terms in there. So we have squares here. We have division by nonlinear terms, so very complex. Also, this system has 2 equilibrium points, one of them being the pendulum in the downward position, and the other one being the pendulum in the upward position. And this upward position, this equilibrium point, is actually an unstable equilibrium point. So if you put the pendulum there and you perturb it slightly, then the pendulum will fall down. That's what it means that it's an unstable equilibrium point. Okay, so our control objective now becomes, we would like to, starting from the downward position, so the pendulum is in the downward position, we would like to swing it up and stabilize it in the upward position. So since this is an unstable equilibrium point, it's quite difficult to gather data for this system. So what we did is we took a controller which is known to stabilize the system, and we generated successful swing up trajectories, where we also added some noise on top of the input to cover more of the behavior of the system and to get more different trajectories as well. And so what we ended up was a data set of 1,000 successful swing up trajectories, each having 100 samples. So we used closed loop data, we call this. So we had a controller which already stabilized the system to generate the data set. We call this closed loop data. Okay, so we trained the model on this and implemented the MPC problem. And what we found was that our controller was also able to successfully swing up the pendulum. And something interesting to note was, even if we initialized the pendulum at different positions, which were not in our data set, so here you can see they all start at 0. Even in this case, the controller was able to successfully swing up the pendulum and also stabilize it there. So that was a very nice result. Also, one thing to notice that we had some constraints being active, so the input could not be larger than 20 newtons. And the controller is, even though it hits the constraint, still it's able to stabilize the system. And here you can actually see it in action. Okay, so now we arrived at the final part of my presentation, where I would like to conclude what we did and give some future research directions. And afterwards, we can have a discussion about this. and also some recommendations maybe.
Yeah. Thank you, Thomas. Do we have any questions from the audience?
The conclusion still has to be done, sorry.
Okay, sorry about that.
Afterwards,
I'm finished.
listen. So to summarize, we have the multi-step DeepONet. We developed a multi-step DeepONet, which is capable of predicting multiple future outputs over multiple time steps by just using one branch network and one evaluation of the network. So the theoretical part of this work was that we developed this adapted version of the universal approximation theorem, which is valid only for operators mapping piecewise constant input signals to sampled outputs. And in addition, we derived the basis of the DeepONet, giving some new insights into the structure. And also this justified that we could draw multiple outputs from this network. So in the future research directions are the following. So what we typically like to do in the systems and control field is to have some stability guarantees. So it's not enough to do simulations and see that the controller is stable. No, beforehand we need to actually have some guarantees that it's going to be stable. And so that's what we would like to do next, to come up with stability guarantees for if you put such a deep neural network, so a deep operator neural network into a predictive control scheme. Under what conditions can you guarantee that the closed loop system will be stable? Secondly, we would like to extend the network by using physics-informed approaches. And this is not so obvious because firstly, we remove the time dependency. And so actually we need that for the physics-informed part. So we need to think about some smart way to do this. Thirdly, we would like to develop some tailored solvers because these networks have a specific structure, which is also now apparent due to this basis. And for this, we might get away with simpler solvers than just using the most complex nonlinear solver, which might be much faster while having the same performance. Finally, we would also like to include a little bit more benchmark examples. So we would also like to compare with LSTM-based MPC, which tries to solve a similar problem, but in a different way. So would like to do that also. So finally, I would like to thank my supervisor, Mircea Lazar, and also Cameros for working together with me and helping me throughout this project. Thank you, and feel free to ask any questions.
Okay. Sorry for interrupting you
No
before.
problem.
Do we have any questions from the audience?
I have a question about the pendulums. You said you have optimal swing up trajectories. Are these made by some other controller?
Yes, indeed. So what we did is we took a controller from the literature, which is known to be able to swing up the pendulum and then also stabilize it. So we use that to generate successful trajectories.
What
Indeed.
controller was that? What is it?
It
Some
was,
kind of MPC or
yeah, no,
human?
it was some energy-based controller. It was also a switching controller. So for the swing up, they used an energy-based controller. Here I have the paper actually that did that. And then if you're close to the upwards position, they switch to a PID controller to stabilize it there.
Yeah, neat, thanks.
Do we have any other question?
Yeah, this is Kyle. I'm a student at Brown. I have one question. I'm not very experienced with control, but I have one question regarding the data that is used here as well. I just wonder, is it possible to train the DeepONet on successful and unsuccessful trajectories, and then maybe you'll be able to learn. Like currently, all the trajectories are successful. Is it
Yeah.
possible that are there other types of unsuccessful data can also be used for training?
Yeah, so for this one, we used indeed only successful trajectories. But if you look, for example, in the van der Pol oscillator, we did not use any successful trajectories in the data set. So we just gave it a random input signal. It didn't stabilize anywhere. So it really learned the behavior basically. So you can indeed use unsuccessful trajectories to get a better
I guess
model of the behavior of your system. So you don't need it, but yeah, we were not able to stabilize the pendulum without these successful trajectories. But I think it might even help to have some unsuccessful to better capture the full dynamics.
Yeah,
like in
makes sense.
contrast to behavioral cloning, you're not learning, you're not imitating whatever was done in the traded data set.
No,
It just
no,
helps you
no.
to flesh out the dynamics better. So anything would help.
Yeah, we're not learning a policy, so really we learn a controller. So it is not trying to imitate the data in any way.
Mm. Yeah, makes sense. Thank you.
So Thomas, if you have a long time sequence, this is not so scalable, right? Because you have to keep adding steps. So have you thought of using state space models like Mamba?
Yeah, not in this work, but I wouldn't actually see how would that
Well, they have the
improve the
control
coding
there.
of multi-step
It just
predictions.
it just advanced the latent space, and it's good for long time
Okay.
sequences.
Okay.
The linear cost.
Yeah.
But it does have the control, and they use the latent space.
So I think it would be interesting actually to compare these two. But why we can actually get away with larger predictions for our case is because the complexity only increases in our output layer. So the only thing that makes it more complex in our case is we have more neurons in the output layers, which are just linear layers. So we do not need to iterate the model more for multi-step predictions with the MS DeepONet.
Right.
That's why it scales actually quite well over the prediction horizon. It's a linear increase actually.
If I can add to that, we have a master student working on the Mamba, and what we see right now is, it's not so easy with initializing the internal state. It's a bit sensitive to that, and we're still working on it to get it as good. Also, Mamba has fixed input sequence, output sequence, so that a little bit
Restrictive.
we try to think how to match, because if your input dimension has different dimension than the output and the horizon is the same, the sequences will not have the same length, and we have to fill it up with something. So
you padded. We did something like that with the FNO. Initially didn't have that, so you just padded with zeros.
yes, we try to. We're actually studying one of your papers where you apply Mamba to learn ODE solutions.
Right. It was very accurate.
For prediction, yes, but the strange thing is that when you apply it in control in closed loop, the performance somehow doesn't match the learning performance.
Okay.
Yet it's still work in progress, so could be our fault.
Yeah.
Also, the LSTM. Do you mean the LSTM, or you can do the sequence to sequence, S to S that they had?
Actually, both. So for LSTM, we were contacted by the professor that used the sequence DeepONet, who put the LSTM in the branch network, and we're trying to compare with that as well.
I see. Great. Lots of things to do.
Yes,
Yes.
for Thomas, it's
Nice. Do we have any other questions from the audience?
There was a discussion. I don't know if Thomas saw. There was like 14 exchanges of text in the chat.
Oh,
Has the issue been resolved? Matthias, I think do you want to bring this up so everybody could follow? Maybe Matthias will turn a...
no, I didn't see it.
Or Tom, maybe Tom.
Yeah, so I was asking if during the training there's some finite time horizon for how well it can predict if time is also given as one of the inputs. They've been misunderstanding the application of the operator network.
Sorry, could you repeat that?
I remember, I mean, so time is also provided as an input for, predicting trajectories, right?
Yeah.
And so during training, do you only provide time that there's some finite value? Obviously, does that mean that at inference time, if you tried to ask it to predict trajectories after that, would it fail?
Yeah, so the multi-step DeepONet, we structure the data set in such a way that the output data set, it's basically a matrix where each column is a trajectory of length n. So the multi-step DeepONet, you're really fixed to this prediction horizon, so you cannot predict further. You can do that with the DeepONet by just iterating over the time, but that's only the traditional DeepONet. So in our case, the prediction horizon is fixed. And that's something you typically do in model predictive control. You choose a fixed prediction horizon, and then you do control with that. So that's why in our case, we were not interested in being able
Makes
to
sense, yeah.
predict multiple length trajectories.
Thank you.
Yeah, no problem.
Matthias, did you want to say something? Yeah.
Yeah, I think now you can hear me.
Yeah.
First, thank you for this very nice talk. I really enjoyed it. Maybe I have one more item for your bucket list.
Okay.
So you showed, you are considering ODEs with input and output.
Yeah.
And in the examples that you showed, let's say the pendulum.
Yeah.
These systems are more than simple ODEs. They are differential algebraic equations. So they have also an algebraic constraint, so-called in orbit. You see the same if you're modeling electronic circuits, something like this. So this is this would be a very important extension. I assume that you have not done this so far, to consider differential algebraic equations with hard constraints. Because then when the solution is a bit off the constraint, you are immediately lost. Yeah, so this is much more challenging, but also much more relevant for the applications.
Okay. But I think still these algebraic differential equations, you can regard them as an operator mapping a sequence to the continuous functions like I showed, right?
Yeah, maybe. This is not my expertise.
Yeah, so I think in theory you could approximate these with the same accuracy. And so you said if a constraint does not exactly hold, you're in trouble with these type of systems.
Yeah, because then the solution becomes immediately unphysical, and then you are doing a prediction starting from an unphysical state, and so it's it's unfeasible solution.
So I think in any case, actually, once you learn the model, you don't really have this physical interpretation afterwards.
Yeah, but often it's also related to stability. When you lose when you step away from the constraint, you're becoming usually more and more unstable.
Okay. Yeah, that's
there is a paper by Amazon. They presented last year, I think, here for DeepONet, where they impose the constraints hard also in the prediction step.
Okay.
So you may want to look at that.
I think I
they do it for PDEs, but ODEs the same thing.
Do you know the title of this paper? It's an
Amazon. I'll find the author. Raj probably knows because I mentioned to Raj many times.
Yes, I'll send you, Thomas. I'll send you.
It's a woman author from Amazon. She gave a talk last March.
Yeah, I actually already have this paper. Good suggestion.
Yeah. Maybe I have a question. In one part where you were discussing about the approximation capabilities of your network.
Yeah.
And did you say that it forms the basis, or did I misheard?
Yeah, so the network, once it's trained, it's simply a function, and this function, yeah, it's actually that's
Maybe do you
actually
have the slide where you were displaying over? Can you go there?
yeah. I shall go back to the slide. I think this one, right?
Maybe. Okay. Yeah, please go ahead.
So that's actually a property of feed-forward fully connected neural networks. That these are the hidden layers, right? So they have activation functions. This one is just a linear transformation of this last hidden layer. So the last hidden layer, it's simply a vector of functions. And if these functions are linearly independent, so apparently they are very likely to be for trained neural networks, then they form actually a basis. So it's just a set of linearly independent.
But this comes from the universal approximation theory, right? Theorem, right? But if I recall correctly, to that this space of all representable neurons form, like in other words, that this is dense, but it's not an exact representation, right? To be the basis, it will have to be an exact representation, and this is an approximation. So essentially, the only thing that we can say is that all the functions represented by these dense neurons is dense in the space of continuous functions. But I'm not sure if saying that it's a basis is too strict, because basis would mean that you have an exact representation, with the approximation theorem doesn't say that.
Yeah, actually, we don't need it to be a basis for the universal approximation theorem. We only need that to extend it to multiple outputs, because if you look into the universal approximation theorem, it's for scalar valued functions. But still, if you look into this universal approximation theorem, you see some function, and this function, yeah, it's basically, maybe it's good if I go there. It is just a linear interpolation of basis functions. So these are the basis functions. They are multiplied with some constant, right? So
Yeah, I mean, yeah, I think I have seen also there's a paper called an adaptive basis viewpoint of
yeah,
neural networks, and
exactly.
where they used it. Yeah, but I think that the general structure would be we can think about basis like functions, because it's an approximation. Because if they would be true basis, you would be an exact representation, which is not, right? So you cannot guarantee that they are linearly independent.
If I can add to that, actually, it depends if it's a basis in a Banach space or in a Hilbert space. So this is, in general, will be a basis in a Banach space, and then it doesn't have to be exact. You will just find the closest point with respect to some operator norm in the Banach space, which is close to your true operator, because the Banach space is not complete. So you can have a basis in a Banach space, which is not complete.
Okay. Okay, well, in that case, for
Yeah,
that
good
one.
point.
Okay, thank you. Do we have any other questions? Apparently, we do not. So thank you, everyone, for your time today. And thank you so much, Thomas, for your great presentation.
Yeah.
And with this, I think we can close the seminar.
Yeah, great. Bye.
Okay,
Thank you,
bye.
everyone. Bye.